Because we're always specifying temperature and pressure with gases, we find it useful to specify a standard temperature and pressure. So standard temperature and pressure is abbreviated STP. You need to know what that means. Standard pressure is 1 atmosphere, which is equal to 760 torr. Standard temperature is 273 Kelvin, 0 degrees Celsius. Really, this should be 273.15 Kelvin, 0 degrees Celsius. STP is useful when we're comparing things, comparing different gases. We've talked about molar mass. The molar mass of something is the mass of 1 mole of that substance. For gases, we find it useful to talk about molar volume. It's the volume of 1 mole. The volume of 1 mole of gas, and typically we're going to express that at STP. So at STP, we've got temperature of 273 Kelvin, a pressure of 1 atmosphere. You do need to remember the temperature and pressure. So 273 Kelvin, 0 degrees Celsius, that's the temperature at which ice melts or water freezes. So that's an easy temperature to achieve in the lab. You don't need technology to do that. All you need is a big vat of ice water. And you take your flask and you put it inside and you wait a few minutes, and you don't even need a thermometer. You know what temperature it is. So that's a very easy temperature to use. Standard pressure is just normal atmospheric pressure. Now that's not necessarily going to be exactly what you need at any given time, but it's at least going to be very close, and it's better than choosing some other random pressure. So let's calculate the volume occupied by 1 mole of gas at STP. So we just did a calculation like this, but not at STP. So the volume was equal to nRT over P. So here we're looking at the volume of 1 mole of gas. So 1 mole at our temperature. Well, first we need R, 8206 liter atmospheres per mole Kelvin. The temperature, 273 Kelvin, divided by the pressure, 1 atmosphere. $22.4 liters. At STP, 1 mole of the gas occupies 22.4 liters, or we can say 22.4 liters per mole. Like with a molar mass, we said, well, it's 58 grams per mole. 22.4 liters per mole at STP. It only works at STP. Any questions? You should remember 22.4. We're going to use it a lot. It's a very useful conversion factor. If you forget the number, it's actually pretty easy to calculate. It's the volume of 1 mole of gas at STP. The molar volume of any gas at STP is 22.4 liters per mole. A mole of gas is Avogadro's number of atoms or molecules, 6.022 times 10 to the 23rd molecules of gas. What the gas is doesn't matter. This isn't true of liquids and solids. The volume of a mole of a solid element is going to be different based on how big the atoms or molecules are. But in a gas, there's a whole bunch of empty space, and so the size of the particles doesn't matter. So I have to tell my Idaho story. No, it's not Idaho, it's Wyoming. So one summer we were driving to visit my parents in Minnesota, and we're driving through Wyoming. It's a beautiful state. Very sparsely populated, though. The entire population of the state is about the same as the population of Fresno. Without Clovis, just Fresno. In the whole state. So at night, you can drive for miles and not see a single light. It's crazy. It's really, really crazy. Okay, so I think of Wyoming as being like a gas, where the molecules are people and they've got lots of space. The size of the people doesn't really matter. If they're all teeny tiny petite things or all the big burly guys, it doesn't really matter. Now, a solid or a liquid is more like people in an elevator. So the elevator says it has a capacity of 10 people. Have you been in our elevator? It's not very big. Is it going to matter how big the people are? Yeah. If you try to get 10 linebackers from the Fresno City football team in there, it's going to be very, very tight. If you put 10 kindergartners in there, there's going to be lots of extra space. In liquids and solids, the amount of particle size, the size of the particles matters, but in a gas, it doesn't. Okay? So here, the volume occupied by a mole of gas is 22.4 liters, regardless of the gas. And that makes gases nice to work with because you can measure their volume and figure out how many moles there are. Now, those gases, different gases will have different masses, right? Because if you're looking at the mass, it's going to be different, even though they take up the same amount of volume. But this is going to be a very useful conversion factor. Here's just an example. Here we have 3 balloons, each 22.4 liters. If this is at STP, there's a mole of helium in here, a mole of xenon in there, a mole of methane in there. Same number of particles, same volume. But how much does the gas in this balloon weigh? How much does a mole of helium weigh? It's on the wall. 4.003 grams. That's, well, as long as you stay on the planet, mass and weight can be used interchangeably. Xenon, how much is that xenon balloon going to weigh?
31.2.
Yeah, 131.3 grams. So this balloon, even though it's the same size, is going to be much heavier because the particles inside of it are heavier. And then this one being full of methane, that's going to be for about 16 grams. Same number of particles, same volume, but the mass is different. We can calculate the density of a gas. Density is mass divided by volume, right? We usually measure gas densities in grams per liter instead of grams per milliliter because they are so much less dense than liquids and solids. So grams per liter gives us more reasonable numbers. If we're trying to calculate the density of a gas, we can do this if we just remember what density is. Density is the mass divided by the volume. So we could say, well, if we have 1 mole, we're going to take the molar mass, the mass of 1 mole, and divide by the molar volume, the volume of 1 mole. So let's try that for nitrogen and helium. So the density of helium would equal the molar mass divided by the molar volume. Yeah, so 4.003 grams per mole divided by the volume, 22.4 liters per mole. The per moles cancel out. And 0.179 grams per liter. Yes?
Is it possible that a problem will say using this volume it will be different than 22.4 for the density?
Yes. In fact, for the density, you're not always going to be calculating the density at STP. You'll usually need to calculate it at a different temperature. And so, or at a different pressure, and then the volume would be different. You can only use the 22.4 at STP. So the density of nitrogen is N2, so the molar mass is 28.02 grams per mole. Again, dividing by the molar volume at STP. 1.25 grams per liter. The density of a gas is directly proportional to its molar mass, because the volume is proportional to the number of particles. So the density is proportional to the molar mass. And so you can derive this equation for the density of a gas with the pressure and the temperature here, and this m being the molar mass. If you can remember that equation and you like that, you go right ahead and use it. It's in the book. I don't like it. So I'm going to show you how I prefer to solve gas density problems. Calculate the density of xenon gas at a pressure of 742 millimeters of mercury and a temperature of 45 degrees Celsius. So I'm going to collect my numbers, because that's always a good idea. So pressure equals 742 millimeters of mercury. Temperature is 45 degrees Celsius. And I have my suspicions that I'm going to have to change some units, but let's make sure. It says calculate the density. So then I ask myself, well, what is density? Density is mass divided by volume. We learned that, I think, in chapter 1. So I need the mass of the gas, and I need to divide by the volume of the gas. They didn't give me any of that. The density is going to be the same whether you have a small amount or a large amount under the same conditions. They didn't tell me what the volume was. They didn't tell me how many moles of gas I have, because I don't actually need that information. But we do need to choose some amount to do the calculations on. So, no, we can't use 22.4 because we're not at STP. So, what's often the easiest is just to choose 1 mole. So I'm just going to say, well, I'm going to calculate the density of 1 mole under these conditions. So if I have 1 mole, what's the mass? It's the molar mass, right? 131.3, right? So 131.3 grams is the mass of 1 mole. You don't even have to really write that down to do the calculation. Then I need to know the volume. Well, I've got a pressure and a temperature, and volume, that should make me think, my ideal gas law. PV equals nRT. If I want to know the volume, I just need to divide both sides by P. The volume is nRT over P. Well, what's N? It's 1 mole, because I chose to do it on that amount. So that would make 1 mole an exact number. It's not going to mess anything up. Then I've got the ideal gas constant. Dang it. Sorry. the units on the ideal gas constant tell me what units I need for the other things. So my temperature, can I use degrees Celsius? No, never degrees Celsius. Plus 273. I don't want to risk doing that in my head. Should be able to, but 273 plus 45, 318. And then I'm going to divide by the pressure. What unit do I need for the pressure? ATM. Yeah, atmospheres. So I've got millimeters of mercury. So I'm going to convert that to atmospheres. 1 atmosphere is 760 millimeters of mercury. And if you have a tendency to reverse the numbers and say 1 millimeter of mercury is 760 atmospheres, step back and think about the barometer and think about that glass tube of mercury that's taller than 1 millimeter. And it was measuring the pressure of the atmosphere where the guy was, right? Which would be 1, not 760 atmospheres. So that should help you get the numbers in the right place. 742 divided by 760. .976 31. Now I know some of you really hate sig figs. If you hate sig figs, just write down more digits than you think. That's always better than not enough. Because if I round this to 1, that's going to screw things up. Okay? So always write down more than you think. And then at the end, round it to 3 or 4 sig figs. That's usually going to be good enough. On exams, especially the multiple choice, there's no points taken off, and I'm not going to try to trick you between two answers where the only difference is that one is the correct number of sig figs and the other is the incorrect. The goal of sig figs is for you to have an understanding of what is a reasonable number of digits. So if you're within 1 or 2, that's usually good enough. But I get hung up on details, and so I always use sig fig rules. So there's my atmospheres. And I check my units, atmospheres are canceling, and the kelvins are canceling, and the moles are canceling. And so this unit is going to be liters for my volume. So I've got 0.08206 times 318 divided by 0.97631. .7 would be 3 sig figs, carry 2 extras, and that is liters. So that's the volume of 1 mole of gas at this pressure and temperature. So that's my volume, so I'm going to put it up here in my density equation. So I've got 131.3 divided by 26.728. My answer is going to have 3 sig figs. So 4.91 grams per liter. Grams per liter is a nice unit. If we did that in millimeters, it would be 4,910 grams per milliliter. And it's always nicer when the numbers are closer to 1. Any questions?
I got slightly different numbers. It's probably saves the full.
Yeah, if you use more digits in the molar mass, you could end up with a slightly different. What did you end up with?
26.74.
26.74. Yeah, so that's going to be very close. There's uncertainty in the 7, and so the difference over there doesn't matter at all. We can also determine the molar mass of a gas experimentally. We're going to do this on Thursday in lab. The idea here is you heat a sample until it becomes a gas. You know the mass of the sample. You measure the temperature, the pressure, and the volume of the gas. And then you can calculate the number of moles. Molar mass is the mass in grams divided by the number of moles. So we've weighed the sample, we know the mass of it, we divide by the number of moles, and we can calculate the molar mass. Let's do an example. Sample of gas has a mass of 827 milligrams. Its volume is 0.270 liters at a temperature of 80 degrees Celsius and a pressure of 975 millimeters of mercury. Find its molar mass. So you can come up with fancy equations for some of these problems, but I think it's better to remember a few basic equations and then just put them together as needed. So this is saying find the molar mass. And so I say to myself, well, what does molar mass mean? Molar mass means the mass in grams divided by the amount in moles. So I need to find the mass of this thing and how many moles are in it. Well, let's take these numbers. So they're giving me the mass, so that's nice. It says the mass is 827 milligrams. Do I want my molar mass in milligrams per mole? No, I want it in grams per mole. So I should convert that. You can do this in your head. Dang it. So 0.827 grams. So there's my mass, so that wasn't too hard. Now I need the amount of gas in moles. Well, they've given me a volume. Volume is 0.270 liters. They've given me a temperature in degrees Celsius. It's very common. Convert that to Kelvin. It's 361. And they gave me a pressure. Is millimeters of mercury going to be a good unit for that? Oh, we need atmospheres. So the pressure is 1.2828 atmospheres. Bless you. So how do I find the moles of a gas?
You have
Sulfur N using which equation?
PV over RT.
Yeah, using the ideal gas law. PV equals nRT. So divide both sides by RT. So I see that N is equal to the pressure times the volume divided by R times the temperature. So my pressure and my volume dividing by R and my temperature, 360. Check the units. I got atmospheres, and I got liters, and I got kelvins. What I've got left here is 1 over moles. It's a compound fraction. If I want to get rid of this fraction within a fraction, I can take what's in the denominator and upside down it, or take the reciprocal. And so that is equal to moles. I was at a football game. The announcer kept saying, Please help us keep our stadium clean by putting your trash in the proper reciprocal. How do you put your trash in a reciprocal? It's a receptacle. He said it more than once. This is still cracking me up. Reciprocal. And it was a proper reciprocal, not an improper reciprocal. Yeah. Things that happen in the nerd brain. 1.2828 times 0.27. Okay, now, I see a lot of craziness happen when people do this math in their calculator. They did everything good and they've got it all written out wrong, and then they miscommunicate with their calculator. Because you look at this and you see that it's this times this, and so you do this times this divided by this times this, and you end up with a very wrong answer. If you want to divide in the bottom, you have to use parentheses. Okay? Because otherwise your calculator will divide by this, and it'll do all of that, and then it'll multiply the whole thing by 361 instead of dividing by 361. So if you want to multiply, use parentheses. What I do is I take this number times this number, divide by this number, divide by that number. So make sure that you can get your calculator to do your bidding. We need 0.1169. 691. And the unit is moles. Did you get that number? Anytime you've got two numbers in the denominator or more, watch out and make sure that you're doing it okay. So there's my moles. I'm going to put this in the denominator up here. So I've got 0.827 divided by 0.011691. Three sig figs is going to round to 70.7 grams per mole.
When I use the full numbers, I got 70.76, so then it round up to 70.8.
Let me check. 0.827 divided by 0.011691871. Is that the one you used?
I guess prior I had 0.0116870.145.
It's 0.1169187.
I must have done something.
That is possible. Yeah, because when you use the whole unrounded moles, I'm still getting 70.7329. Is this a reasonable number for a molar mass? Sometimes a question like that's hard to answer, so then let's see if we can answer a question. What would be an unreasonable number? How about 0.05? Could you have a molar mass that's 0.05 grams per mole? No. What's the smallest molar mass you can have? 1. Hydrogen atoms are 1 gram per mole. So molar masses have to be 1 or larger. So 70.7, that's probably reasonable. Pardon me? Oh, what element is this? It's probably a compound. And because if we look at metals, gallium is 69.7, which is close to this, but that won't be a gas at 88 degrees Celsius.
But if you see gas, like
Oh, it could be something like diethyl ether, or it would have to be a compound of nonmetals. Yeah.
What are you using this here?
So when you add 273, is it 273.15 or just 273?
It's best to do 273.15.
Because I did the calculations again, and I got a slightly different answer, but I got 70.75. So it was closer to the lower number, but it's still rounded up. So. Let me just look at it with you doing great.
Yeah, we'll look at it. So here's an example that's more like what we're going to do in lab. An inorganic chemist isolates a colorless liquid. An organic chemist, there's a difference. Isolates a colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask and puts the flask in boiling water, which vaporizes the liquid and fills the flask with gas. She closes the flask and reweighs it. Her data is given below. Calculate the molar mass of the liquid. So this is very much like what we're going to do in lab. We're going to put a liquid into a flask, a volatile liquid, meaning it vaporizes easily. And so we're going to put the liquid into this flask. We know what the mass of the empty flask is. We put it into a large beaker of boiling water, which causes it to heat up. As the liquid heats up, it's going to turn into a gas. It's going to vaporize, and as it vaporizes, it will start to escape from the flask. And so it's going to fill up the flask, and we're going to let it go until it's all vaporized. So at this point, she seals off the flask to keep the gas in there, takes it out of the hot water. You let the liquid cool down, and because you can't weigh something hot on the balance. And you weigh the flask again, and it weighs more than it did empty because it's got a little bit of liquid in it. That liquid was the gas that filled the flask. We measure the volume of the flask. We can measure the temperature of the water, which we can assume is the temperature of the gas inside. The pressure, if that flask is open, what's the pressure inside compared to outside? It's the same, right? So the pressure is measured using something like this. This little weather station measures the atmospheric pressure. So that's going to be the pressure inside the flask. So we have the volume, we have the temperature, we have the pressure. We're trying to find the molar mass. So molar mass is the mass in grams divided by the amount of gas in moles. What's the mass of the gas? We've got a mass of the flask and a mass of the flask with the gas in it. We need the difference, right? Subtract. 78.416 minus 77.834, 0.582 grams. Both of those had 3 decimal places, and so the result has 3 decimal places. So that's our mass, 0.582 grams. How do we calculate the moles? PV equals nRT. So N equals PV over RT, that's the rearranged form. We need our pressure to be in atmospheres. So that's the conversion factor. If you want to write it this way, write it 754 over 760 atmospheres. That's okay. You can just do that math when you're doing the rest of the math. Can we convert milliliters to liters without writing everything out? What's it going to be? 0.213. We're moving the decimal point 3 places. Liter is a big unit, so the number has to be smaller. This is the small unit, the number has to be bigger. R is the same. temperature. Okay, here the temperature was given as 100.0. If I just add 273, I'm going to lose a significant figure on that. And so here's a place where I think it is definitely a good idea to use the full number. Personally, I prefer that they just always use the full number, but they didn't ask me. Okay? 754 divided by 760 times 0.213 divided by 0.08206 divided by 373.15 . That's what my calculator shows me. So I've got 3 sig figs in some things and 4 in others, so that result would have 3 sig figs. That's my moles. Bring it up here. So 84.3 grams per mole. Any questions?